Welcome back, everyone. Chemistry 1001, Introductory Chemistry. We just got done talking about writing equilibrium constants. We write equilibrium constants based on the balanced chemical equation. We have a balanced chemical equation here. We see a metal oxide, manganese oxide, reacting with acid, and we have chloride, also chloride anion available here. And then we get magnesium metal that's liberated from the solid into the aqueous solution. We get Cl2 gas and we get H2O. So this equation is not quite balanced. We need to put a, I believe we need a 2 here. We need this must be 2. Then we are balanced. So let me just mention, just in general, metal oxides tend to be basic. So if you have something that's basic, what would you react it with? Acid. And that's what we do in this reaction. So anytime you hear about metals, metals tend to form a base oxide, an oxide that is basic, meaning that it can be reacted with acids. So we oxidize a metal. Oftentimes we get a solid and we can liberate that with acid. There's so many different chemical reactions. Anyhow, we do have a balanced equation. We didn't have to worry about water, however, because water will not appear in this reaction because it's in such high supply, because this is it is an aqueous solution. So water's everywhere. We can ignore H2O in this reaction, but we wanted to make sure the equation was balanced. Manganese oxide is a solid. It reacts with acid solution. Maybe it's hydrochloric acid, and produces the manganese 2 plus cation, which is floating around solution. It's no longer sitting at the bottom of the beaker. We get chlorine gas bubbling off. So manganese oxide will, with acid and chloride, will generate chlorine gas. So there's a way to make chlorine gas, which is probably not too safe to do. It's green and toxic. Manganese oxide is a metal oxide, and it's basic, so it does react with acid. Acids and bases tend to react. H2O liquid is a product, but it's negligible, so we don't even have to think about it in the equilibrium expression. We need a balanced chemical equation to write the equilibrium expression. We can do that now. And this here, we can ignore this. However, everything is balanced according to the way this is written. And this is written a little bit differently. The charges here, 4 plus and 2 minus gives us 2 plus, and manganese is 2 plus. So everything balances with the charges too. Not only do the chemical species need to balance, but the charges need to balance. So we come up with the KEQ. The products go on top. Just as a review, the products go on top. We put an exponent to whatever number is in front of the product manganese. There is only a 1 here, so that is only raised to the first power. We have Cl2. There is only a 1 here. It's not showing, but so that's only to the exponent 1. We don't need to show that. Then we put the reactants in the denominator, and the reactants is the H plus proton, which there's 4 of them here, so we have to put a 4 here for the exponent. Then we have chlorine as another reactant, and it has a coefficient of 2, so we have to put 2 as the exponent. Now we have the KEQ, and if we get the molarities of each of these species, which can be a lot of experimental work, we can figure out what the KEQ is, or we can look it up for a specific temperature in a book and find out if we get more products or if we get more reactants. If we have a very high KEQ, a large number like 100, we get a lot of products. If we have a really small number like 0.0001, then we have a lot of reactants present at equilibrium. Equilibrium is when the reaction happens and the rates go to 0. The rates, I should say, the rate of change goes to 0. The forward rate and the reverse rate are actually equal to 1. And when you divide them, they'll be equal to 1. So interpreting equilibrium constants or interpreting equilibrium constant KEQ, you have a reversible arrow in the chemical equation to show that equilibrium exists, that this reaction does not go to completion. So if we see that, then we can have an equilibrium constant. And only then can we have an equilibrium constant. A reaction that has just one arrow, one direction, has no equilibrium constant to speak of. So we can interpret this, and this is the way the experts say KEQ. If it's greater than 1 times 10 to the third, a large value of KEQ indicates the numerators of the product, that the product term is higher than the denominator, which is a reactant term. So at equilibrium, there's mostly product present. If KEQ is less than 1 times 10 to the negative third, a small number, we have a small, indicates the numerator is rather small compared to the denominator, and the reactant term dominates. And at equilibrium, we have mostly reactants present and way less products. If we have KEQ between 1 times 10 to the negative third and 1 times 10 to the third, the equilibrium mixture contains significant concentrations of both reactants and products. We have to consider them relative. Okay. This is a little different looking at the graph. Let's just start with the graph. And here previously we had rate of reaction on the y-axis. We had rate, but now we just have concentration. Okay. So the concentration, the rates become equal, but the concentrations, of course, do not become equal. So this graph is a little different than what we saw earlier. And the time here, this is the progression of the reaction, which is the same as what we saw when we were looking at rate on the y-axis and time and progression of the reaction on the x-axis. Here we have concentration, and how does the concentration change with respect to time? So we have this reaction of NO2 gas, which is toxic. It's reddish brown. We don't want to breathe this in, unlike N2O, which is laughing gas. And we can make N2O4, which is less toxic. So this reaction might be useful to get rid of some of this toxic gas. I'm not so sure about N2O4, but this NO2 is a orangish brown colored gas. And so we probably can see the color change as it goes to N2O4. This is a reversible reaction. Both are gases. The reactant and the product are gases. And we proceed to equilibrium, whatever the case, whatever the KEQ value is, that will be the ratio of products to reactant. This graph tells us that at equilibrium, when the rate is no longer, when the concentrations are no longer changing overall, we know that the rate of product formation equals the rate of the reactants reforming. But the concentrations are different, as they would be in many reactions. And N2O4 is in greater concentration at equilibrium than NO2. So what would you know? That the KEQ, you can think about this, the KEQ certainly has to be greater than 1 because the products are in the numerator. They'll be in greater concentration than the reactant nitrogen dioxide. As the reaction first starts, note that there is no product. There's no product here. That's 0. And you have just reactants. And then as the reaction goes, the reactants are reduced and the products are increased. And then when the rate of reaction becomes equal, the forward reaction becomes the same as the reverse reaction. So we have Kr, which is the reverse. We have Kf, which is the forward reaction. They end up equaling each other. When Kf and Kr equal each other, so we say Kf equals Kr, Kr, then we are at equilibrium. The rates are the same. They're not 0. The overall rate change is 0, but the forward and reverse reaction equal the same, and therefore Kf over Kr or Kr over Kf equals 1. And therefore we know we're at equilibrium, and we will have more N2O4 than concentrations of the reactant of NO2. So that's just how this reaction goes with those conditions. KEQs can be looked up in books, right? KR, KF is different than big capital KEQ. Totally different things. Rates versus reaction concentrations. We could have a gas reaction, and we could have hydrogen iodic acid reacting to give us H2 gas and I2, and we know that H2 gas and I2 can reform the hydroiodic acid. This is a strong acid somewhat, but in a gas phase, it behaves a little bit different. Remember, what phase are we in? Gas, gas, gas. And you don't have to memorize that hydroiodic acid is a strong acid that goes it goes to completion in a liquid phase. This is a gas phase. It may behave differently in a gas phase than it does in an aqueous phase. To make it simple, just look at the balanced chemical equation to see what happens. This has a reversible arrow, so the reaction can go both ways. The forward and the reverse reaction can become equal, therefore equaling 1 when we divide either rate constant for the reaction equals 1. We don't have to worry about it. All we have to worry about now is KEQ. We don't have to worry about rates of reaction. What we need is the concentrations. Maybe we get those from color change. We get one of the reactant, the only reactant, hydroiodic acid, which is going to go in the denominator, which is going to be Hi2. And then we get the two products that are formed, which is H2 gas and I2 gas. Those are the products. There are no coefficients in front of the products, it's just a 1, so we don't have to raise the exponent to anything but 1, which is what it is here. And then we have the reactant, which is going to go in the denominator. The reactant is in the denominator, and it's 0.54, but it has a 2 out in front of it in the balanced chemical equation. So you have to put a 2, you have to put it to the exponent 2 with respect to the molarity or the concentration. Molarity and concentration are the same. We do the math, we get 10.1, and it's unitless because moles per liter or molarity all cancels out. What that tells us, 10.1 means there's going to be a little bit more of the product at equilibrium than there will be of the reactant. So we know which direction the concentrations lie upon that the reaction lies towards this side, right? The reaction lies towards this side. How do we know that? Because of this 10.1. There's more products than reactants at equilibrium. So we just saw a numerical application of the equilibrium constant, the K value. Now let's look at something that controls some of these reactions. We don't have to worry too much about the rate because we're just going to think about how the concentrations change. So let's just think about the concentrations in the reaction and think about qualitative judgments. Le Chatelier's principle says that if there's a stress placed on a system at equilibrium, the system will respond by altering the equilibrium compositions in such a way as to minimize the stress. So the rate of the reaction temporarily changes to reestablish the equilibrium. Don't worry about the rate. I'm just trying to tell you there's a process to this. Let's think about what this statement means. If reactants and products are present in fixed volume and more NH3 is added into the container, the system will be stressed. So let's just think about it in simplistic terms. We increase the concentration of ammonia gas. If we increase the concentration of ammonia gas, we upset that KEQ that we looked at earlier. The molarity of ammonia is going to temporarily go up. And the KEQ is a law. It tells us the ratio, and that ratio must be obeyed. It's like what we learned about the law of composition, the law of definite proportions. KEQ is the same idea in many regards, but it's expressed in a number, and that number must be maintained. So if we increase the products, we're going to increase the numerator, and therefore we're going to change the KEQ to what they call a KQ value, and that's going to have to change eventually to be equal to KEQ as it was previously. So ammonia being added at equilibrium is going to force reactants to be made. You're going to make more reactants to offset the increased concentration at NH3. That's just the law of the universe. being applied. So KEQ is a law and it is obeyed, so the reaction shifts to again meet the calculated value defined in tables or handbooks. That's why this is so important in industry, whether it be pharmacology and making drugs, making food products, petroleum products, oils, whatever it's going to be, electronics, any chemical involved, Le Chatelier's principle, gases, this is going to be applicable. Now, if we were to do, let's change color, and we'll change the color to blue, and um, let's say we add into gas. We add into gas. So we had a whole bunch of into gas. Which way will that shift the reaction? Will it shift it to the left or will it shift it to the right? Well, in this case, instead of being shifted to the reactants, we added more of the reactant. That's going to force we're going to force the reaction to shift to the right. It's going to shift to the right and make more products in this case. It's going to do the very opposite. So now do you see what you can do if you have a cheap reactant and you need a certain product in industry? You can just keep pumping that cheap reactant in and end up using up most of the other reactant, which might be more expensive. So say that H2 gas is the more expensive of the two, and it costs you a lot of money to buy H2 gas. You can pump into gas, and you can force all of that H2 gas to be reacted by putting just a ton of excess of into gas, so that this will end up reacting, which makes sense. More concentration with one of the reactants means that it's going to be easier for the other reactant to run into that reactant and form the product, okay, at the conditions specified. Anyhow, Le Chatelier's principle is really like a game. It's kind of fun to think about because it's so applicable in biochemistry, in industry. Le Chatelier's principle is something you should never forget, right? Hopefully you don't forget this class, Introductory to Chemistry. So if adding NH3 to the system causes stress, to relieve the stress, it wants to break up into the reactant molecules, and NH3 comes together to form N2 and 3H2 to relieve that added concentration of NH3. Now, if we add NO2 or H2 to the system, or we add both to relieve stress, we're going to want to make NH3 gas, right? Now, there's always a limit. Some student might say, well, wait a second. What if I keep adding N2 gas forever, but no more H2 gas? Well, then you would run out of H2 gas eventually, okay? So apply common sense and apply this theoretical frame, okay? Product introduce the reaction shifts to the left, right? So if you introduce more ammonia, you shift to the left and you make reactants. If you introduce more of the reactants, you shift to the right and you make more product, okay? So this holds true in many situations. Effective concentration. So we see this effective concentration. It's going to temporarily change the relationship between the product and the reactants in the calculation of KQ, which KEQ is going to be a law that's got to be met. So even if you temporarily change the amount of concentrations, it's going to go back to KEQ and reproduce that number, that ratio, that set ratio that we know to be. So the system will react to the stress to return to the concentrations to the appropriate ratio that KEQ gives you or indicates. Okay. This is a neat reaction. The color can tell us some things about what's going on. We know the reactant is red and we know that the product is yellow. So when we're more reddish, we probably have more reactants present. If the solution is red, we probably have more reactants present. If the solution is yellow, we probably have more products present. Okay, so we look at B, we know that we must therefore be on the left-hand side and we must have more reactants, right? More reactants. But if we're yellow, so if we're yellow, we're going to be more towards the product side. Of course, Fe3 plus is yellow. the iron thiocyanide is red. The free iron 3+ species is yellow, where these two are no longer in a complex ion formation. You haven't learned a whole lot about this yet, but what happens is this thiocyanate feeds electrons into iron and actually forms a compound that is sort of a mix between covalent and ionic, and they call it a complex ion formation. And we're not going to get into that too much. If you take inorganic chemistry or Gen Chem 2, you will get into that. So let's read exactly what it says, so we don't misinterpret this. Beaker A, reaction at equilibrium. So at equilibrium, it looks kind of orangish red. So it's hard to say. Maybe there's more of the product, or maybe there's more of the reactant. It's kind of in both worlds. So maybe they're kind of even in concentration, right? It's kind of hard to say. Is this more red or more orange? Or excuse me, is this more red or more yellow? If you say it's more yellow, then of course you got more products at equilibrium. If you say that it's more red, well, then you have more reactants at equilibrium. For beaker B, it shifts to reactants with more red color. So beaker B, you definitely have more of this iron thiocyanate present, this 2+ species. So you're on the reactant side, and the KEQ would be what? It would be small because this is large. Now, if you're in beaker C, you shift to products with the loss of red color. So you're yellow, so you're over on the product side. So your KEQ, or your KQ calculation, we don't know what the KQ is, would be high at this time. We'd have to do some math, but kind of look at this qualitatively to see what's going on and make sense of it. So effective heat, endothermic reactions require heat to go in as a reactant. You need heat to go into these molecules, and the heat gets stored in the bonds that get formed in the product. So that's an endothermic reaction. The very opposite of combustion and some of the reactions we've seen that are more spontaneous. Endothermic reactions, we put heat in, we put 39 kilocalories, some amount of joules, kilocalories, whatever we want to call it, energy, kinetic energy. And these molecules end up reacting and forming into an O2 gas. And this is wrong. This can't be right here. This has got to be something like NO. This has got to be something like NO2. So maybe this is nitric oxide. And so this becomes 2 here. And that would be, we wouldn't want that to be 2. We'll have to look. The reaction is messed up. Another typo by the company. I'll have to find out what's going on there. That's wrong. That's okay, though. We can still go along with this. We'd have to have 2 nitrogen, 2 oxygen atoms, and there we would go. So we'll say it's N2 plus 2O2 reacting with this, and this is 2NO2. And nitrogen dioxide is toxic. It's brown and orange. And if this is the case, because there's no way we could get ammonia here, we have no hydrogen. So you have to be careful. Look for those problems if you ever see those as a chemist, as someone in medicine. And so this reaction here, if we add more heat, to the reactant side, we push it to the right. Okay. But what if we were to cool this? What if we were to cool this and take out heat? So if we went the other way, let's change the arrow so it makes it easier. We already have enough confusion with the pointer option pen, but we want to change the ink color and we want red. I want red. So we take out heat and we go this way, or we take out the heat. So if we take out the heat, what's going to happen is the products are going to unform to make reactants, and it's going to go this direction because we're taking away a reactant. We're removing some of the heat, and therefore we're shifting the product back to the reactant and where some heat can be liberated. So the reaction will shift to the right if heat is added, but the reaction, if you cooled the reaction would shift to the left. Okay, if we removed heat. So this is a result of removing heat, right? So think about that. Make sure you understand it. Effects of pressure for gas. Okay, now we're just thinking about a reaction that involves gases. We don't include liquids or solids in this assessment. And again, we're going to use Le Chatelier's principle of relieving stress. So we add more products, we're going to end up getting more reactants made. If we add more reactants, we're going to shift the reaction to make more products. So if we add pressure, we're going to have to relieve that pressure. And if we reduce the pressure, we're going to have to see how that also affects the reaction. So we have to think about the relative number of gas moles of reactant and product. Remember, that's what what does a balanced chemical equation tell us? It tells us obviously the makeup of the molecules, individual molecules, how bonds are broken, how bonds are reformed. But we also know what is a gas, what is a liquid, etc. And we can figure out the relative number of gas reactants versus the number of gas products. So when the pressure goes up, we shift to the side with fewer moles of gas because we're pushing things together, and so that forces the side that has the least amount of gas particles to be formed. But if the pressure goes down, we shift to the side where more moles of gas can be formed. And remember, it's not complete, it's just a shift. We have to remember that. So effect of pressure example, we go back to the ammonia synthesis reaction with nitrogen gas and hydrogen gas. So if we increase the pressure, which way will the equilibrium go? Well, we have, I'm going to turn on the laser. Here we have only one gas mole, and then we have 3. So we have 4 moles of gas here versus only 2 moles of gas here. So if we increase the pressure, we're going to decisively move towards the product side because there's only 2 moles of gas here. So we increase the pressure, it favors decreased volume and more product. So we will have, in this case, we will make more ammonia gas. Now, what about a different type of reaction? If we increase the pressure here, we have 2 moles of hydroiodic acid, and here we only have 1 and 2 moles of gas for the product. So there's not going to be any change here. There's not going to be any change. It'll have no effect because both sides have 2 moles of gas. Right? So we have 2 moles, but in this case, we have 2 moles of products versus 4 moles of reactants. We increase the pressure, we're going to shift to the side with fewer moles. So increased pressure makes more of the product in this case. We have to think about the reaction we're looking at, but this bottom reaction, we get nothing. No shift in equilibrium as both reactant and product have 2 moles of gas, 2 moles of hydroiodic acid, and 2 moles of 1 mole of hydrogen gas and 1 mole of diatomic iodine gas. So be careful. This can be a little tricky. Effects of catalysts. What does a catalyst do? A catalyst does not directly show up as a reactant. It doesn't show up as a product. You often do not see it in a balanced chemical equation. The catalyst does not become part of the product. The catalyst is not part of the reactant. What it does is help a reaction to occur. It can increase the rate of the forward reaction and increase the rate of the reverse reaction depending on what direction it's being pushed to. So the equilibrium composition, it does not change the KEQ. A catalyst does not change the chemical equilibrium value. The KEQ does not change because of the catalyst. What it does is it affects the rate. The rate is faster, both forward and reverse. So it gets to equilibrium much quicker through a catalyst. And that, my friends, is the end of the slide set. Catalysts, just to let you know, are very important in industry. People use catalysts to make them lots and lots of money because catalysts shorten the cycle for chemical manufacturing. And as we know in business, time is money, money is time, and that's just the world. Thank you for listening, and that is the end. This has been Chemistry 1001, Introductory Chemistry.